Read through this question. Determine what you think the answer is. If you watched the last video, this is very similar. We have a block of mass M resting on the floor of the elevator. So our free body diagram, the dot representing the block, force of gravity, the weight of the block is pulling straight downwards. The earth is pulling the block towards the center of the earth. Normal force, the floor is pushing up on the block. So the free body diagram is the same. Any acceleration this block experiences in the y direction is because of the net force in the y direction. So normal force up, mg down, that represents the net force. When we divide by mass, that represents acceleration. So to answer this question and to determine if the normal force is equal to mg, or bigger or smaller, we have to read the question to find out if there's acceleration. For me, I always have to revisit the question. So it tells us that the acceleration is upwards. The picture tells us it is also moving upwards. Picture tells us the acceleration is pointing upwards. That means the net force also has to point upwards. So to add n and mg and get a result that points upwards, the normal force n must be greater than mg. If we were getting to the point of calculating, I would rearrange what we wrote over here. N minus mg would equal the mass of this block times that acceleration it is experiencing in that y direction. Total side note, if you've ever been in an elevator, or perhaps just go to a building that has an elevator, if you were standing in the elevator, so you started at rest, you start moving upwards and speeding up at the same time. Remember, velocity and acceleration in the same direction would be representative of that speeding, going faster in the upward direction. It's only a short period of time that this happens for, but we feel a bit heavier, or we feel like we're getting pressed into the floor. We would be experiencing the normal force acting on us. We would be pulled towards the earth, equal to the force of our weight, our mg. What we feel is the normal force. Sometimes we refer to this a feeling as what is called apparent weight. For example, if we were standing on a scale in the elevator, it would be the scale that was producing the normal force instead of the floor of the elevator. The scale would read or show the normal force. The scale is showing how hard you're pushing down on it because that's how hard it has to push up on you. So if you were in an elevator standing on a scale, during the short period of time where the elevator starts moving upwards and speeds up for a really short period of time, the reading on the scale would be higher than normal. It would show more than your weight. How much more depends upon the actual value of the acceleration, but it would show higher. The opposite is true as well. If you're still moving upwards, but the elevator's slowing down to stop at the floor, it's going to. Slowing down, the acceleration would be opposite. So if we were still in the elevator moving up, but slowing to stop, the acceleration would have to point down, which means the net force has to point down, which means mg, your actual force of gravity, has to be bigger than the normal force in that case. If you were still standing on the scale, the reading on the scale in that short period of time would be smaller than your actual weight. If you've ever been in an elevator and sorry, that's a terrible stick figure. That moment the elevator just starts to move downwards, if you jump at that moment, for a split second, you get a feeling of weightlessness. Now that's just a split second. It's not a continual feeling. Very teeny tiny second. That's because for just a split second, if you have jumped upwards, you have disconnected your feet from the floor, so that for that very teeny tiny short period of time, there's no normal force on you. No normal force means you feel weightless. So kind of interesting, the concepts that relate together here.